In 1990, humanity received a photograph that permanently altered our perspective of our place in the universe. A fragile speck of dust caught in a beam of scattered sunlight. Carl Sagan immortalized it as the pale blue dot. But this historic snapshot wasn't just a triumph of space exploration, it was a farewell. Because mere moments after capturing that image, Voyager 1's cameras were powered down forever. For 36 years, our most distant emissary has been flying completely blind. Today, Voyager 1 is plunging into the uncharted territory of interstellar space, a staggering 24 billion kilometers from Earth. And incredibly, it is still talking to us, but if this spacecraft is still functioning, why did we purposefully blind it? And more importantly, if we could somehow send a command to Voyager 1 to open its frozen eyes today, what would it show us lurking in that endless darkness? Welcome back to the Cosmic Scale. Today, we are taking a journey to the absolute edge of human reach. To understand the darkness Voyager 1 faces today, we have to look back at its fiery beginning. Voyager wasn't just a random shot in the dark. In the early 1970s, astronomers realized that Jupiter, Saturn, Uranus, and Neptune were moving into a rare geometric alignment, a cosmic phenomenon that happens only once every 176 years. This alignment meant a spacecraft could use the gravitational pull of one planet to slingshot itself to the next, saving years of travel time and immense amounts of fuel. NASA seized this once-in-a-species opportunity. Launched in 1977, Voyager 1 was tasked with giving us our first real look at Jupiter and Saturn. And it over-delivered. We saw the violent swirling storms of Jupiter and the razor-thin, mesmerizing rings of Saturn in unprecedented detail. But Saturn was the turning point. As Voyager 1 swung past the ringed giant, the planet's massive gravity gave the probe a final, violent kick. It was flung out of the orbital plane of our solar system at a blistering 61,000 kilometers per hour. In 2012, it made history again, crossing the heliopause, the boundary where the sun's solar winds give way to the interstellar medium. It became the first human-made object to touch the space between the stars. But as it crossed this monumental threshold, it did so with its eyes tightly shut. Before we explore why the cameras were killed, we have to clear up a massive misconception about what those cameras actually were. When we think of a space camera, we picture high-resolution digital sensors. But remember, Voyager launched in 1977. There were no CMOS sensors, no digital memory cards. Voyager's eyes were built on Vidicon imaging tubes, technology closer to a bulky vintage CRT television than a modern DSLR. Furthermore, these cameras couldn't even shoot in color. To create the iconic color images we know today, Voyager had to take multiple black and white photos of the exact same target through different colored glass filters: red, green, and blue. These separate images were beamed back to Earth, where scientists manually stacked them to create a single color composite. And then there was the transmission problem. Today, you can send a 4K video across the globe in seconds. Voyager, currently 24 billion kilometers away, has to whisper its data across the void using a 23-watt radio, about the power of a refrigerator light bulb. At its current distance and data rate, downloading a single 1 megabyte image would take roughly 15 hours. Every single photograph required a massive expenditure of time, data bandwidth, and most importantly, energy. Energy is the harsh, unforgiving currency of deep space. Out where Voyager lives, the sun is just a particularly bright star. Solar panels are entirely useless. Instead, Voyager relies on a nuclear battery called an RTG, a radioisotope thermoelectric generator. It converts the heat from decaying plutonium-238 into electricity. But radioactive decay means that every single year, Voyager produces less power than the year before. NASA engineers faced a brutal ultimatum. If they left the cameras on, the 40-watt power drain would have killed the spacecraft decades ago. With no more planets to photograph, keeping the cameras active made no scientific sense. So they made the ultimate sacrifice. They didn't just turn the cameras off. They wiped the incredibly complex software that ran them from Voyager's tiny onboard memory to make room for new code. They even shut off the internal electric heaters that kept the camera lenses from freezing. For 36 years, Voyager's cameras have been suspended in a deep freeze of nearly minus 50 degrees Celsius. To turn them back on today is impossible. The power is gone. The software is deleted. The hardware is permanently frozen. But let's play the ultimate game of what if. Let's imagine we could instantly beam the software back, magically generate enough power, thaw out the lenses, and command Voyager 1 to take a picture of interstellar space. What would we see? You might expect to see a cinematic tapestry of glowing nebulas, massive alien galaxies, or uncharted rogue planets. But the reality of space is defined by its emptiness. The first photo from interstellar space would be almost entirely uniformly black. You might catch the faint glimmer of a few distant stars, but otherwise it would be a portrait of an unimaginably vast void. The universe is not crowded. It is profoundly isolated. However, if Voyager's cameras could see beyond the human visual spectrum, specifically into ultraviolet light, that pitch-black photo would suddenly ignite. Voyager is currently plowing through an invisible cosmic structure known as the hydrogen wall. This is the ultimate battlefield, where the outbound solar wind from our sun violently crashes into the incoming interstellar medium. This collision causes hydrogen atoms to emit a faint ultraviolet glow. If we could photograph it, we would see our spacecraft sailing through a massive, glowing celestial fog at the edge of our solar system. What if we turned the camera around? What if we tried to recreate the pale blue dot from 24 billion kilometers away? We would see the sun. It wouldn't be a large disk anymore, but it would still be a fiercely brilliant point of light, hundreds of times brighter than a full moon on Earth. But Earth? We wouldn't see it at all. From that extreme distance, the Earth is so close to the sun that it would be entirely swallowed by the intense solar glare. Even in 1990, taking the pale blue dot was a massive risk that could have burned out the camera sensors. Today, Earth would be a microscopic fraction of a pixel, completely invisible against the blinding light of our home star. Furthermore, traveling at 61,000 kilometers per hour for nearly 50 years takes a toll. The camera lenses have endured decades of cosmic radiation and impacts from microscopic space dust. Any image we took today would likely be distorted, scratched, and heavily blurred. You might think that traveling 24 billion kilometers would at least change the shape of the constellations, but the universe is so incomprehensibly large that Voyager's journey is less than a millimeter on a cosmic marathon. Proxima Centauri, our nearest neighboring star, is still 40 trillion kilometers away. From Voyager's window, the stars look exactly the same as they do from your backyard. In a few short years, the plutonium heart of Voyager 1 will decay to the point where it can no longer power its most basic scientific instruments. One by one, they will shut down. The radio transmitter will fall silent. But even when the craft goes completely dark, its journey will not end. Bolted to its side is the Golden Record, a time capsule containing the sounds of our planet, our music, our biology, and a map back to our tiny blue home. Voyager 1 will drift through the eternal night, a silent, blind ambassador of the human race, destined to outlive the very hands that built it. Thanks for watching. If you want to explore more of the universe's greatest mysteries, make sure to subscribe and stay tuned right here on The Cosmic Scale. We'll see you in the next one.